Hi everybody. Today we're going to look at some more proofs by induction, and we're finally out of the realm of looking at proofs where they're always a sum is equal to some formula. Now we're in a sort of more generic setting. I thought I'd first use a screencast to sort of show you the results I'm interested in proving today, and then we'll go out to the whiteboard and do the proofs in marker because that's easier. Okay, so I've got a Sage worksheet open. You don't need to see my head all this time. Make that a little bit smaller. I got the Sage worksheet open, and I wanted to illustrate for you an interesting little phenomenon. So first I'm just going to need to declare a variable for Sage, because it's used to using x as the variable when you're doing math. I should probably mention to you that this is sort of an interesting phenomenon. In a computer program, usually some sequence of letters or numbers is treated as a computer variable, but in this particular thing, it needs to be able to treat certain sequences of letters, numbers, and whatever as mathematical variables, and it needs to make a distinction between variables that might hold data and the variables that are meant to be, part of a symbolic expression that it can work with. So that's what I'm doing right there. I'm declaring to the Sage program that I is the name of a variable, and the reason I put quotes I inside is you've also got to tell it how to display the thing, so to display it as itself. But sometimes you do things differently than that. Right, so I don't want to dwell on that. So we've got, did I execute that? Shift Enter, yeah. We've got a variable now. I'm going to run a little loop that, let's go from 0 to 19, a range of 20. And what we're going to do in here is look at powers of 6. Wait a minute, I guess I better tell it to actually output that. Print 6 to the I, right? When I hit go, sure, we see powers of 6. Now, you might notice that, except for that first one, they all end in a 6. They really all end in 6s. So let me print another thing right along next to it. You might think I'm going to print this mod 10 in order to pick up those 6s, but I'm not. I'm going to print 6 to the I power mod 5. The percent symbol is the Python and many other languages use that operator for mod. And, well, not surprisingly, we see that you get all 1s when you look at the value of 6 to the I mod 5. Even the initial one is 1 mod 5, but all these 6s are 1 greater than a multiple of 5. That's clear. Yeah, so is that surprising that 6 to the I power is always 1 modulo 5? Well, let me show you, for instance, what happens to 7 to the I power. 7 is, let's see, 1, 7, 49, 343. Yeah, those are the powers of 7, and their values mod 5 go 1, 2, 4, 3, 1, 2, 4, 3. They're in a certain order, but they're just all over the map. The only thing I'm not seeing is 0 mod 7, which kind of makes sense because, sorry, I just said that wrong, 0 mod 5. There's no 5s in the factorization of this number. It's going to be a lot of 7s, no 5s, so how could it ever get 0 mod 5? You get 0 mod 5 precisely when you're a multiple of 5, and that's not going to happen here. But we get every other option, which is good. So what's the difference between 6 to the I and 7 to the I? Let me change the modulus for us here, make that a 6 this time. I've got 7 to the I, but then I'm going to print its value mod 6. And it's 1s again. You see what's going on there? If you don't, here's another one that should definitely nail it for us. How about if I put in 17 to the I power and then 17 to the I power mod 16. Run. Always 1s. Yeah, so what's going on there? Hopefully that example made it clear. the number that I was raising to the I power was 1 mod the modulus, right? So if I multiply a whole bunch of 1s, I of them together, it's not going to matter. I'll still have a 1. So this is a kind of a cool result, which we can prove by induction. I'm going to go back out to the whiteboard in a second and prove that by induction. But first, I want to show you the other proof, or the sort of background on the other proof we're going to work on Wednesday. For that, I made this picture in a drawing package. This is why they call me old school. This drawing package I'm using is probably 30 years old, maybe older. But I laid out a checkerboard in here. Did I get the right number of squares? Yeah, 8 by 8 checkerboard. And these L-shaped things are objects that are known as trominos. So a tromino, actually technically they're L trominos because there's two kinds of trominos. You can have L-shaped ones like this and long ones that are like 3 squares long. Notice that these babies are sized just correctly for laying across the squares of the checkerboard. So each tromino covers 3 squares. Now, I hope you get that that's a sort of a bad pun, that a tromino is a trio that makes up like a domino but with 3. Right? So 3 squares joined together gives you one of these trominos, although I distorted them slightly so that you can see the underlying checkerboard. Okay, so why do I have these trominos out here, and why do I have a checkerboard out here? Anytime you have an object like these, the generic term for them is polyominoes. They're multiple ominoes. Dominoes is like just the 2 squares joined together, but a tromino is 3 squares joined together. There's a popular game called Tetris. Tetris is objects are 4 squares joined together. Tetrominoes, technically. Anyway, if you've got dominoes or trominos or whatever knows, you can ask a question about whether they can be used to tile something. And so, for instance, I meant to copy that object into place, not to just move it. Let me save myself a copy of it down here. I could put this kind in there, and they would sort of nestle together. And what else? I could put this one over here. Do you think I'll be able to eventually cover this checkerboard thing here with these trominos? Well, at first there doesn't seem to be any impediment. You've just got to try to make sure you don't, get yourself stuck. Like, what do I mean by that? If I took this one here and tried to lay it right there, I've created a spot that I can't really tile. Well, I suppose I could, but I do that at the expense of having something dangling off the edge of the board, which, it would fall off if this was really in the real world. So we don't want that. All right, so well, I guess I want to kill that one too, don't I? There. Yeah, so what do you think? Could we tile this checkerboard with trominos? There's an easy necessary condition that isn't fulfilled. You see, the number of squares on a domino board, or sorry, on a checkerboard, is a power of 2. This is, in fact, there's 2 to the 8th power, 64 squares on a checkerboard, and each tromino covers 3 of them, but 3 doesn't divide into 64. In fact, well, that's enough, right? You know that if you did divide 3 into 64, it would go 9 times, I think, no, more than that. 21 times, but you'd be at 63 then, there'd be 1 left over. Yeah. So, here's a new question. Could I take 1 square away? Let me see if I can manage to do that. Let's see, I'll just change the color to red. Okay. And we will red out this square right here. I didn't red out the whole thing. Gosh, my anal retentiveness is on top of me now. Okay, there it is, it's gone. So, except for that 1 square, we should now have an even multiple of 3. Can I tile the chessboard with that? Using these trombones, can I tile everybody except this one square? So that's the second question. We're going to prove that yes, you can. It depends on the size of the chessboard. So there's a general question. What about instead of an 8x8 board, maybe I want to do this on a Canadian style one where they use 10x10. That's not for chess, it's for checkers, but you get the point. You can have different size checkerboards, and you can always ask this question about whether you'd be able to tile it with trombones. All right, so we're going to go out to the whiteboard and to have a look at these 2 proofs. One is that if we're looking at powers of n, they will always be 1 modulo n minus 1. And the other is that to prove that we can always tile a chessboard of a certain size with trombones. Okay, I admit the first one might seem reasonable. The second one is very much recreational math, but it's still fun. And so I'm going to stop apologizing and go do this. Yeah, so the first result, I'm going to state it formally first, and then we'll go ahead through with the proof. What is the theorem? I'm going to do maybe a specific example of it first, and then we'll try to do it a second with in the general. All right, so let's put it this way. If I look at, say, 6 to the n power, and I subtract 1 from that, because 6 to the n would always be 1 modulo 5 when I take away 1, that's something that's always divisible by 5. So 5 is always a divisor of 6 to the n minus 1. How would this statement be quantified? That's for all n in the natural numbers. 5 divides 6 to the n minus 1. So there's our theorem. Kind of strangely pushed to the left because I waited to the end to figure out what the quantifier is, but okay, we'll live with that. Proof. I'm going to proceed by induction. And you got to think about how induction is going to work. Well, maybe not. Maybe we'll be rote about it. What's the first thing we do when we're going to do an induction proof? Figure out what the base case is. This theorem, here's the beginning of the proof. I do like to put it in that little parenthetical note that tells me tells my reader what style of proof they're about to witness. Until we're working by induction. And our base case, well, this was for all n in the naturals. I'm one of those people that takes 0 to be the smallest natural number. So what we just note is that 6 to the 0 power minus 1 is equal to 0. And it's true. Anything divides 0. So the base case is pretty easily dealt with. Just got to make sure that doesn't look like I'm writing the number 510. Maybe I'll make my divide sign a little taller. Okay. Well, what about the inductive step? What we're going to be doing in the inductive step, I'm not going to put in the we want to show type sentence, but let's just talk about it. What are we trying to do? We show that if 5 divides 6 to the k minus 1, then 5 will divide, well, the power 1 higher up, 6 to the k plus 1 minus 1. So to get started on that, we're going to assume the if part. Assume that the statement is true at this k stage. Assume, what about k? K is greater than 0. It is a natural number. And that, I'm just going to abbreviate natural number with the hashtag, but the word number should have really been written out. I'm just out of space. Assume k is a particular but arbitrarily chosen natural number such that, and our such that is going to be that the inductive hypothesis is true. That is, such that 5 does divide into 6 to the k minus 1. Now we want to try to get that 5 divides 6 to the k plus 1 minus 1. And so well, maybe it's not too crazy then that we would say, well, how do I get that 6 to the k into a 6 to the k plus 1? I'd have to multiply by 6. All right. So let's consider the number 6 to the k plus 1 minus 1. It is equal to 6 times 6 to the k minus 1. That's just algebra, basic fact, right? And somehow I would like to pull out the thing we know about, that 6 to the k minus 1 is divisible by 5. Well, it turns out you can have this happen, pull out that desired thing by just thinking about how to re-express what 6 is. And it feels like an unjustified step, but 6 is 5 plus 1, isn't it? So that's sorry, put the equal sign in the wrong spot. The previous thing is equal to 5 plus 1 times 6 to the k minus 1. Well, that's interesting, isn't it? Because if I distribute the 6 to the k over this sum, I will get 5 times 6 to the k plus 1 times 6 to the k, and then there'll be that additional minus 1. All right, well, I'm going to put an end to that sentence. So, by the way, check that this is still a grammatical sentence. It says, consider 6 to the k plus 1 minus 1, which is equal to 6 times 6 to the k minus 1, blah, 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 which is equal to blank, which is equal to... That's a sentence. It may be a little bit of a run-on sentence because it's got multiple verbs in it, but it's still, I guess, is okay. Stylistically, that's what we end up doing. All right. Now, I know that this piece of it, 6 to the k minus 1, is divisible by 5. So let's tell our audience that. 5 divides 6 to the k minus 1. In fact, that's the inductive hypothesis. I'm abbreviating again just because of space constraints, but probably really shouldn't abbreviate in a proof. Anyway, 5 divides 6 to the k minus 1, that tells you, by the definition of divisibility, there is an integer. Gotta pick a good letter here. I've been using k's for the power. The original statement, I believe, had an n in it, so let's use m. But this is the integer that exists because of the definition of divisibility. Gotta finally kill off this bottom line so that we can continue. There is an integer m such that 6 to the k minus 1 is equal to 5 times m. Okay, great. So that means, looking at this original consider sentence, 6 to the k minus 1 can be re-expressed as 5 times something plus 5 times m that we just got. Let's just do that for our reader. Thus, 6 to the k plus 1 minus 1 equals 5 times 6 to the k plus 5 times m. If you need a justification for that, it's simply substitution. And since 6 to the k and m are both integers, 6 to the k, well, should I really do the one more step of factoring out the 5? Yeah, I probably should have done one more bit of algebra here. But I'm going to jump to the conclusion. This isn't very far. We've got a multiple of 5 plus another multiple of 5. Therefore, 6 to the k plus 1 minus 1 is divisible by 5. Let's write it in using the divisibility symbol. And write a tiny QED in the corner because we're out of space. That's a pretty slick little proof. I mean, really the stroke of genius, if you will, is going from writing 6 to writing 5 plus 1. That's what makes it happen. And you know, that may seem unmotivated right now, but after a while you go, well, yeah, that's sort of a natural thing to do because I can peel off a 1, which is going to get me the inductive hypothesis, and a 5, which is good for us in this case because it was all about divisibility by 5. That's what led us to that scenario where we have 5 times something plus 5 times something else. All right, let's look at this this Tromenose business. Keep forgetting that I'm going to edit these, so you're not going to have to watch me erase the board. Yeah. So okay. Here's the theorem. It's interesting. Anytime you have a chessboard which has a power of 2 as its sides, so a 2 to the n by 2 to the n chessboard, I guess we might take n to, if I think about this as n equals 0, I'm probably going to be upset because n equals 0, this would be a 1 by 1 chessboard. Yeah, okay, so let's start off with a 2 to the 1 by 2 to the 1 chessboard. That is a 2 to the n by 2 to the n chessboard with 1 square removed. Well, such a thing can be tiled perfectly, that is completely covered with nothing hanging off the edge, by L. Tromenose. The phrase when we're talking about that is tiled. We're tiling the chessboard with the Tromenose. So now, that's sort of the right base case, but I haven't said we're starting the proof yet. This is a first write proof, and we are going to work by induction. Now I can write base case. What's the base case look like? Well, what n value, the smallest n that makes sense is, because if n is 0, I really don't want to deal with it. I mean, it's actually true in that case too, but I'm going to use n equals 1 as the base case, because it seems less trivial. If n is 1, we're talking about a 2 by 2 chessboard with 1 square removed. So it's 2 by 2, like that. Maybe I'll color some of them black and some of them white. And it's going to be covered, oh wait, there's 1 square removed. How about it doesn't kind of matter, right? Because you can always just turn it in place. So I'm going to say take out the top right corner, take that guy away. It can be covered with an L Tromenose. Sure it can. Exactly 1 Tromenose fits right across the thing, like so. Make sense? So yeah, a picture literally suffices to tell us that the base case is true. Right, so the base case is handled, but how am I going to proceed to work inductively? Personally, I think this is good advice. If you're not clear on how to proceed, play around with the next case up from the base case. Maybe play around with the next couple of cases until you start to notice a pattern. So let's take a look at the case when n is 2. That is a 4x4 checkerboard. I'm trying to carefully divide up my square into 16 little sub-squares. Now, the way this is stated in terms of, sort of pictures, there's a lot of symmetries involved. If you think about it, I mean, there's 16 different squares I could pick to be the one that we prune away so that we're not dealing with it. But there's really only 3. That is, there's 3 things to think about. Either it's in the corner that we remove the thing, and it could be that corner or this corner, but those are all the same. You just rotate the board, right? Or it could be along the side. And again, that one and this one is the same. Just flip the board over or spin it, So there, or here. Those are the 3 locations really that you need to think about, because any other square on the thing could be thought of as a rotation of one of these, or maybe a flip. So let's do this first one. Let's do the one where the corner square is taken away. Excuse me. So, can we cover this thing with dominoes? Well, yeah, but I'm not sure. Well, we should do it just to sort of get a sense for, what's going on. I feel like I want to surround that guy. And how about then I just kind of keep that pattern going, like a chevron that heads towards the corner. That was nice. Oh, yeah, that was really nice because, I got that strip across the middle, but what got left over was a tromino in this corner and a tromino in that corner. So we were able to do it with the missing square being in the corner. Let me try that again. Wow, that was kind of cool that it just worked out. All right. So what if the prune away the one we're not going to need to tile is along the side instead of in the corner? Well, I can tell you something for sure I'm going to have to do is put one in like this, right? I've got to use the projection of one of these trominoes to get to that square. But then, what? I've just finished this upper corner off, and I can play the same game I did before. Take these ones on the diagonal that head me down towards the corner, and then we're left over with a tromino in each of the other corners of the board, which we can fill in, and boom, it's done. We've tiled with trominoes again. So far, so good. You want to try it one more time? I'll tell you what, we can get away with just a little bit of erasing and see how to do the next case. There's the next case, without loss of generality, it's when the missing tile is right there. The missing square is right is sort of in the inside. And you see what you're going to do then is just use, did it in black instead of green, but anyway, a tromino up in that corner. So yeah, that's doable too. So what do these all have in common? Well, I'll just point out to you, there's one domino that I could have left in place in all of them. It's this one in the middle. And that actually is a really good spot to think about because we're trying to work by induction, which means we want to refer to the previous stage. And the previous stage, this is the 4x4 case, the previous stage is right here. Yeah, it's that little 2x2 guy. That's a 2x2 with one square removed. Now, unfortunately, there's other 2x2s in here that don't have a square removed. That is, until we knock this guy on, and then it's the same thing as having removed one square from each of these other little 2x2s. Once you make that insight, that's really the meat of the heart of the matter. You're ready to prove the thing inductively. Okay, so you're probably going to prove this inductively, but also include some pictures to make it clear to people what's going on. So we'll consider a 2 to the n plus 1, or 2 to the k plus 1, I think I'll use. By 2 to the k plus 1 chessboard with one tile removed. One square, I should say, removed. This square happens in one of 4 places. So we can always rotate the board until it happens in, say, the upper right corner, what we might think of as quadrant 1. That leads to a great abbreviation you'll start seeing in more advanced proofs. It's this, WLOG. That stands for without loss of generality, meaning we haven't changed that we're dealing with an arbitrary setting by making this assumption. You don't have to write this out like I'm doing now, just say WLOG, but this first time I wanted to tell you what it means. So without loss of generality, the one square that's been removed lies in the upper right corner. So what we're going to do is break this 2 to the k plus 1 by 2 to the k plus 1 chessboard up into 4 things of half the size. Well, yeah, just set 4 2 to the k by 2 to the k chessboards. And place a single tromino in a certain orientation at the sort of point where they all meet. How does this single tromino work? We saw it a second ago when I was working the example. It's got to cover one square in each of these subboards that we're using, except for the one place in the upper right where we've already got a missing square from the original presumption that there was one missing square in our full-size board. So we want that one tromino placed so that it covers one square in all but the upper right. I think I can get away with just saying the other three boards. Oops, boards with an O first. Yeah, so let's get that picture I was referring to. Yeah, so I don't want to fill in the squares here. I just want us to think about the overall shape. This is going to be a great big 2 to the k plus 1 by 2 to the k thing. So that is the side length of this thing is 2 to the k plus 1. The side length of one of these four corners is 2 to the k. And we've placed a single tromino right here at the middle so that its corners, or its three squares, cover one square in each of the boards, the upper left, the bottom left, and the bottom right. And there was also, somewhere in here, there's a single square removed. So each of these subboards now can be tiled by trominos because that's what the inductive hypothesis says. Isn't that strange? You know it can be done, no matter what size they are. I think I'm not going to even write that up at this point. You just say, all right, this one can be tiled separately from this one, separately from this one, and separately from this one. The tiling of those four things together gives you a tiling of the whole 2 to the k plus 1 by 2 to the k plus 1 board. So that's our last proof for today. Remember, Friday is a holiday, so there's no school Friday. So have a good weekend and stay safe, and I'll see you next week on Monday.